quite a bit about industry in the last couple of talks, and I want to pull up that statistic that Robert showed at the very beginning. Industry is only half the people in that audience, and I would be tempted to say that also the software that is being developed at the moment is probably half industry, half basic research, half developed by universities. And as this graphic also shows, like only 40% are really identifying themselves as computer scientists, and there's a very diverse crowd here that apparently is interested in quantum computing software. So one of the big problems that we saw over the last couple of years is when you look at academic software, so not the industry thing, not the next Qiskit or something like that, there are two cool things. One is there are novel ideas in there. So basic research is really driving the forefront of what we can do in quantum computing. And there's impressive results in there. You see new compiler passes around that beat the existing state of the art every day, essentially. But this all comes with a lot of caveats, and I'm just gonna unroll them right here. And I'm pretty sure all of you have encountered this at some point. Like, you've encountered just prototypes that you can hardly use. You have a hard time installing a package. The package is just provided as is. No installation instructions, no documentation. You have absolutely no idea how to use these phenomenal results, how to replicate them, and how to incorporate that into something much bigger. On the other side of this, there's industry software, and we've heard quite a few of the buzzwords that I'm going to list here right now. You have a fully fledged implementation that is actually developed to be used by others, and not only just produces numbers in a paper, which is great per se, but it's only part of the whole story. So you have continuous integration, you have continuous deployment, you have certain standards of quality that you put on your software, and it's a real spectrum from the left to the right. So like, it's a huge one indeed. And we are a research chair, so we are technically, per standard, per definition, we're on the left-hand side. But over the last couple of years, we've been trying to build something that is more situated on the right-hand side. We're trying to build software tools that people can actually use that are still yielding impressive results and that are at the forefront of research. And maybe a quick show of hand, who of you in here has heard about the Munich Quantum Toolkit before? Seems like we're doing not too bad of a job of marketing our toolkit. That's great to see already. For those of you who do not know what we do and what that toolkit is, essentially it is a collection of software tools that can go from topics like application, like supporting end users in developing their applications, essentially all the way down to hardware and EDA. That's where we come from as a research chair. We're the chair for design automation, so we are very close to that per se. And it literally covers all the topics in between, whether that is simulation, that is compilation, that is verification. Also error correction and fault tolerance is getting more and more attention, and we need software for that, desperately. And all of these are naturally supported by data structures and core methods. So core computer science techniques that everyone should be aware of, or everyone should be using to design efficient software. One thing I want to make very clear for those who do not know the Munich Quantum Toolkit or are not aware of that, this is not supposed to be the next Qiskit. This is not supposed to be end-to-end, solves every problem. What we're trying to do here is really to find the weak spots and pain points in the software stack for quantum computing, and to develop tools that are automated and efficient for these pain points, so that hopefully we get utility of quantum computing a little sooner. To illustrate that, what it means to be a collection of tools, I'll just quickly show you. This is a current list of the open source tools that we host on our GitHub page that we also maintained over quite a couple of years, and I'll tell you a little bit more about that in the short-term future. These are categorized by kind of these arrows you saw before, this roadmap from applications to hardware, and there's a tool for quite some interesting problems in there. I've talked about this quite a few times, and those of you who knew the Munich Quantum Toolkit before have probably also seen that slide before. So I want to do something a little bit different for this presentation right here in this audience. But first, before I do this, if you're more on the paper reading side and want to get a brief glimpse of what this is, and this talk is not enough for you, there's a new paper on that you can check out. It's on the archive, and you'll probably find it if you Google MQT Handbook. Nice introduction maybe to the topic and to our view on things. But I said I wanted to do something different. So what I want to do is I want to give you a very, very short history of how the Munich Quantum Toolkit came to be and where we started and where we ended up. Because we didn't end up with all these these standards, these development best practices and stuff like that, we started on that very left-hand side where we just did cool research methods. And these are all, we started in C++, they needed to be fast. We're in the design automation community, everyone wants to be faster than that person before them. So we decided, yeah, let's do it in C++, let's develop some great projects. Okay, so far so good, develop something fast. Just because it's fast doesn't mean it's actually working. So we figured out, yeah, we need some testing, we need some continuous integration, we need some continuous deployment. Essentially, the whole phenomenon, I bet you all stumble upon this. It works on my machine, but someone else raised, doesn't work, doesn't compile, throws all kinds of errors, seg faults here, seg faults there. So what we set up, well, what we noticed is, hey, GitHub has all this cool infrastructure to test on various systems. You can test on Linux, you can test on macOS, on Windows, and you can make sure that your stuff actually works so that you hopefully can prevent that people just raise issues, tell you, hey, it doesn't work on my system. All right, fast and tested, good. Doesn't mean someone can really understand it and the code base can still be quite a mess. So what we noticed when people started to look into our code is they weren't really understanding what's going on. So what we definitely made sure as a next step is to introduce some common formatting, some common linting, to make sure that code quality that we ship to someone or that someone is using is actually up to a certain standard. There are cool tools for that, so if you look at Clang Format or Clang Tidy, they support you automatically. You get automatic formatting, you get good tips actually of how you should modernize your code maybe. If you're used to C programming, transitioning to C++, it gives you quite some good tips on how you can use the standard library to make something great. It's fast, tested, but also has a certain quality and can be understood. That was roughly the time where really more people started into looking into our projects. So we noticed that just pushing to main on changes isn't really communicating a lot to the people that are using the tools. It's breaking left and right. That's not how you should do things. So what we really tried to adopt, and what I can only recommend people to adopt, is first of all, do open source software so people can actually see what you're doing. First call to action. But also please make use of all the nice features that GitHub provides you with, like issues, like pull requests, like releases. They make it so much easier to communicate with your target audience, with the people that are actually trying to use your tools. That helped quite a bit to get better communication and to set better expectations of what's going on. As you notice, this is all still C++ at the very top. And quick show of hands, who had problems compiling C++ at one time or the other? Probably everyone raises their hand now. At least if you have a computer science background, you definitely have. We heard it before from Blake. Rust is also kind of painful to compile at times. And we noticed we need to make this easier for people to actually use our tools, because otherwise they're just struggling. Natural thing to do, as many people actually do by now, is to introduce Python bindings for your code. You bind to the language that the community is using. Everyone in the quantum computing community probably touches Python almost on a daily basis still. And I'm not quite sure that will go away, at least on the front end side. But at least in the back end, it should all still be fast. On the front end, it should be accessible. But what comes with having a C++ backend that is exposed to Python is people still need to compile your package. So we noticed they still had issues running things or getting things to run or to compile or to build. But Josh mentioned it I think in the Q&A in the morning session, that as a packager or as you developing tools, you can help people make their life a little bit easier. The buzzword there is pre-built wheels, so you can take care of the building and you can ship binary wheels to the people that they can literally just pip install, and that is it. They get the convenience of having just a pip install, but all the performance of C++. It's one of my favorite phrases that probably all of our tools are just pip install away. If you're wondering about that UV in there, I won't spend too many minutes about that. If you haven't heard about that project, it's a project by a company called Astral. Google that real quick or note it down and check it out if you're working with Python and you're annoyed by the Python ecosystem. They're doing great stuff. Just check it out. So, easy to install, fast, but yeah, people still didn't know how to use our tools. So what we set up is documentation. And just to be very clear, for many of the industry folks in here, it's totally clear that this is all common standard. But on the academic side, yeah, it's rough at times. So setting that up took a while, and also retrofitting documentation to all the things we developed took quite a substantial effort, but it paid off in the end. Last but certainly not least, we already heard it, the ecosystem is moving quite fast. So a big topic in all of this is maintenance. How do you actually maintain a tool so that it stays compatible and doesn't break in the next 1 or 2 months with the next Qiskit release or whatever? And this is a big ask. Like, I bet all of you remember a project where you checked out an archive paper. It said like, hey, code is open source. And you opened the GitHub page and it said like, last commit 3 years ago. And you already knew you can give up. Like, it's not gonna work with the current pace of the quantum ecosystem. So, one thing that I didn't mention in here is also that once you have a tool, you wanna integrate it somewhere. So I wanna quickly highlight a couple things where we try to integrate the Munich Quantum Toolkit with the broader ecosystem so that people can actually use what we were building. And the first thing directly connects to the previous talk. It's Qiskit. And it's something that I'm particularly proud of because, I don't know, 6-7 years back, everyone was using Qiskit, literally. Like, most of the people were comfortable using Qiskit. They weren't comfortable using our tools. But what we made possible is that they could just use their Qiskit circuits, push them through our tools, and get Qiskit circuits back. And the thing I'm most proud of, we started supporting Qiskit when it was version 0.17 something. And for those of you who are not aware of that, Qiskit went up to 0.46 until it reached stable 1.0 and now 1.2. So that's over 30 big releases that happened in the last years. And I think in not a single one of those, it took us more than a week to fix our packages and make them compatible again so that people can still keep on using them with their common ecosystem. That was quite an effort, but again, it paid off. And hopefully with the stability of the ecosystem kind of increasing, these hero efforts become lower and lower. So it gets easier to do that and to justify doing it. Next thing, also kind of on the opposite side of the spectrum, is an integration with Planck. It's a service platform, it's kind of a marketplace for services. And what we just did is we made our tools available as service on that platform. You can actually, it's quite nice, you can have a workflow builder where you just click together services that pass around inputs and outputs, and you can really click together your whole workflow. The MQT is part of that. And we've heard about PennyLane before, this morning. Some of our data sets, I'll talk about this a bit later at the end of my talk, are available to PennyLane users so they can use them in their benchmarks, in their tests, to see whether everything they do is working. Now, one thing, there's an empty spot right there, and that is something I'm particularly proud of, and it is the work on the Munich Quantum Software Stack that we, as a community in Munich, that means the Munich Quantum Valley, this is a photo of the recent review meeting we had just a couple weeks back, quite a few people there. This is the effort that we do in the Munich Quantum Valley to build a common software stack for all of this ecosystem. And I'd like to highlight a particular group of people that drive this effort substantially forward. Please, quick show of hands. Laura, Martin, I don't know, Martin, were you around? Olke, Ershman, Yannick, myself, don't mind that. Robert, please, quick show of hands. These are the people that make that possible. So they make it possible that I'm standing here and talking to you. So what I'm gonna talk about in the next couple minutes is mostly props to them. I'm just the one pitching it and pitching our vision when it comes to this whole Munich Quantum Software Stack. So this is an effort that is driven by the Leibniz Supercomputing Center, by the research chair of Martin Schulz at TUM, and by our research chair. This kind of trio of people tries to realize this big picture of, you have domain experts that want to use quantum computing, and you have quantum devices on the one side, and the big question in the room is how to go from one to the other. How can you actually realize a useful application on one of those devices? Even if we have good devices, we still need a way to realize the applications on them. And right now, the current state of the art kind of looks a bit like this. There are a gazillion different options to go from left to right. Some of them I might have put a warning sign there, some of them might not even work, some of them stop right in the middle somewhere. It's a bit of a mess. And the overall goal that we would like to have, and that many people share that vision or that goal, is we would want to have a quantum computing software stack that brings together applications to some common representation and then targets multiple different platforms. We've heard about all the buzzwords, we've heard about MLR, about QAR, LLVM, and all of that. I'm not going to repeat that part. We've heard a lot about Q2Q, we've heard a lot about Catalyst, and these kind of infrastructures. But I want to talk about one important question in this picture, or at least actually two, but let me start with one. And that's actually the question, how do we connect the software side with the hardware side in there, and the software developers with the hardware developers? These typically come from very different disciplines. Like on the right-hand side, you have physicists, you have experimentalists. On the left-hand side, you have computer scientists. They're typically not that knowledgeable in physics. And these people speak quite different languages. We'll actually have a panel later this evening, last session of the day, that targets this question a little more. How can you actually communicate between those people? How can you connect them? How can you make sure that they speak the same language, or that they mean the same problem when they talk? But let me kind of simplify the overall picture and demonstrate something that we've been working on for the last couple of weeks and months. On the left, you see a common program, very generic. On the right, you see a couple of devices, and you want to execute that program on that device. And this is a very, very simplistic view, but bear with me. First of all, what you do is you do something that is device agnostic. You compile something, you optimize, you do this over and over, and at a certain point in time, you choose a device. You choose something where you want to run on, and then you do some device-specific optimization. Again, in a loop, we saw this in the previous talk, and then you want to run on the device. But alone in that simple picture, there's quite some questions involved. Like, what are the available devices? What is their status? Are they even online? What are the constraints and the characteristics of a particular device I'm running on? How do I actually submit a job to that machine? And how is the machine calibrated? How up to date is that data? How long can I rely on that data? All questions that at the moment may be answered individually for each machine, but definitely not in a common format or a common standard. And that's essentially exactly what we're trying to build. What you see here is the so-called QDMI interface, stands for Quantum Device Management Interface. You'll hear this often enough so that you remember it, hopefully. And its purpose is really that it allows you to submit jobs uniformly in a standard fashion. It allows you to get results back from these machines. And one of the most important parts, probably, it allows you to query information about these devices and their characteristics and constraints, so that you could feed this either directly into a compiler, or you could aggregate them, because this is a low-level interface. So you might not want to work with this directly, but you might have a library, and there's another acronym in there, FOMAC, Figures of Merits and Constraints. We don't like the name either, but we haven't come up with a better one. So if you have a better name for that concept of aggregating information and preparing it for people to use to make it actually usable, or more convenient to use, please approach us. That's the overall structure and the purpose of QDMI. I want to give you a brief deep dive of how the structure of that interface looks like. And it mainly has three components. On the one hand, you have devices. On the other hand, you have clients. And the third part of this is a driver that mediates between clients and the devices. And then there's a couple of interfaces. One of them is the query interface that allows you to query properties of the device, of its operations, of its qubits, and so on and so forth. The second one is the interface for controlling the device, sending jobs there, getting results back, and many, many more tasks, but that's a general idea. And then there's this session interface that allows you to do user management, access control, that essentially pipes these devices to the client so they can use it. And we've spent quite a couple weeks on that and months on that. And we've talked to a lot of people, probably also in this room, but this wasn't public yet. But I think by now we're at a point in time where we feel comfortable to talk about all of this and to get your feedback on this, because we really like this to be a community standard. So if you want to check it out and want to know the details, you can literally just go to that link on the very top, and you can see the GitHub repositories. And most importantly, this is all open source. Oops. This apparently still seems to be private. Let me maybe quickly change that. So, danger zone, very, very dangerous, but let's go. I want to make this public. I have read that. Oh, no. And there it is. There it currently is now. So that for us, this is a big step. don't consider this the full release of all of this. It is just we're at a point in time where we'd like to get your feedback on what we've been building here and what we've been discussing internally and with many of the hardware vendors and the people developing software. So please get in touch with us, give us your feedback, give us your criticism. We need that and we try to improve on that. And a full release is planned for later this year, so look out for that and look out on the GitHub repository. But let me take it back to this big picture, because the right-hand side is only one part. So like there's an interface from the software to the hardware, but there's also the left-hand side of this whole picture. So there's domain experts that want to use quantum computing for something useful. And the big question in here is, how do we actually support them so that they don't have to become quantum computing experts in order to use a quantum computer? And one of the main things we've done in this regard as a research chair, what we noticed is, it's really tough to get benchmarks for all of this. It's really tough to test your stuff from a very high level down to compiling to an actual device. So what we've built is, in the beginning, a Python tool that you can simply pip install, as all of our tools. It's open source, so you can check it out, and you can use it to generate a huge amount of circuits on various levels with various gate sets. Compiled to various different devices with different qubit technologies, and it's a simple call, get benchmark, you pass all the parameters, you get your circuit. It's nice, but even Python, as usable as it is, and as convenient as it is too inconvenient for some. So what we decided to do is we decided to wrap a service around this that hosts the interface on a website that you could just go on. You have your checkboxes. This is the algorithm selection. There's quite a few algorithms in there. You just select your algorithms, you select the number of qubits you want, and then you have a second part of the interface where you choose the level of circuit you want, you choose the gate set you want, you choose the device you want, and you can even choose compiler options you want to compile that circuit to that certain device. So whatever you need as benchmark, you can get that. If there's something in there, the list of applications is growing. The list of supported devices is growing, and also the list of compilers is growing. But if something is in there that you're missing, then please get in touch with us. We're happy to integrate these tools in there. If you need benchmarks for your hardware and you have a very specific gate set, reach out to us. We'll incorporate you. If you have specific applications that you'd like to benchmark on certain circuits, there's so many notions of benchmark in here that we'll probably hear across the next 2 days. This should be able to facilitate many of them. And what we've seen is this has become adopted quite a bit. So since 1.5 years ago, it has almost reached the 3-digit GitHub stars and citation count for the research paper. If you don't mind, give us a star so we reach that 100. Just kidding. But that map also shows that it is really used worldwide. Benchmarks are downloaded worldwide, and it kind of shows the demand for these circuits that are easy to get. So these are the downloads from the service, from the website, not from the Python package itself. This is just that service is really being used, and we see the demand for that. But we also see, like I just mentioned, that there's more to just generating circuits. There's just more to simply saying tick, 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 give me the circuit, because you still have to do something with the circuit. So what this is a small teaser of what we're currently thinking about and trying to build, is in addition to circuit generation, you can also maybe simulate something or execute that on a real quantum device with all the different configurations options I showed you before, with all that infrastructure in mind, literally by just clicking a couple buttons, maybe providing your API token or your credit card somewhere, but just joking. That's what we're currently trying to build. This will be up soonish, so keep an eye out on the MQT Bench website and on all the news that will come soon. With that, I'd actually like to wrap this up a little bit, and excuse the shameless plug, but I like to bring a couple of highlights of what we've been doing over the last couple of years. And we've been doing this really for a couple of years. Robert has been around in the quantum domain since 15 years, since roughly 15 years, maybe plus. I've been around for 5 years plus, so we have some experience in developing quantum computing software. And that software is not only software, it's also based on research. It is based on excellent results, over 100 papers, and also some awards, which are nice. But even more importantly, the community seems to be using our tools. So the Munich Quantum Toolkit just passed over 1 million, even 1.5 million downloads on PyPI, and over 750 stars on GitHub. So it seems that people like what we're doing. And I hope this goes to show that tying back to the beginning of the talk, that one can transcend academic research into practice, into industry strength software, and that's kind of what we do. So if you want to know more about that, that's the website for you, and with that, thanks.